All right, so we're on our last section here in Unit 7, and this is going to use that formula that we developed in yesterday's material. So before we begin, we need to talk about converging and diverging series. So let's just do a brief, and this is really for like the most basic definition of converge and diverge for what we need. What it boils down to is if an infinite series converges, then we say it has a sum. If it diverges, it approaches either positive or a negative infinity, we say it doesn't have a sum. Now, again, these are not the best, most mathematical definitions, but they'll do for what we need. We need to decide if our series that we're looking at is going to have a sum or if it's not going to have a sum. So let's start by deciding whether it converges, has a sum, or diverges, doesn't have a sum. So let's start rules for determining. It's pretty basic. First of all, up here, it talks about infinite series. So the rules for determining if it converges, I'm going to briefly talk about a finite series, which is one that ends, but the ones that we're going to be dealing with on the back page, the ones where we're actually going to be finding the sum, those are all going to be infinite. Okay, so rules for determining whether it converges or diverges. Number one, you have to decide if it is finite or infinite. Finite just means it has an end. Infinite means it goes on forever and ever and ever. And you can see like the dot, dot, dots, or some of them that have sigma notation on the bottom, point one out kind of way down here on the bottom, that it approaches infinity. And so we know then that it's infinite. So that's the one thing that I'm going to look for. If it is finite, it always converges. It will always have a sum. If it is infinite, then we have some other criteria that need to be met. If it is infinite and arithmetic, it automatically diverges. But if it is infinite geometric, then sometimes it diverges, sometimes it converges. So when we look for what comes next, I'm sort of making a lame attempt at a flowchart here, I guess. So finite always converges. Infinite arithmetic always diverges. But infinite geometric, we have to look at our common ratio. If the absolute value of r is less than 1, that's kind of what we talked about in yesterday's notes. Remember seeing that -1 is less than r is less than 1 was kind of the constraints that we put on it, so that when we raised it to the nth power, the denominator would get infinitely large, and then we would end up having terms that approach 0. So if our absolute r fits that, then it diverges. Nope, I'm sorry, then it converges. Then it has a sum. Then we can use the sum formula. I apologize for that. But if r is outside of that, meaning, oh, how do I want to put it? Absolute r, I don't know. Yeah, we can do it that way. We can say absolute r is greater than or equal to 1, then it diverges. Then it's going to approach infinity, and it's not going to have a sum. back to the infinite arithmetic, hopefully that makes a little bit of sense, because if we're arithmetic, we're either going to be continually growing positive and it's going to get infinitely large, or we're going to continually grow in the negative direction by adding a negative each time, and therefore we will approach negative infinity. Whereas the geometric, when you multiply each time, you have that possibility of term by term by term, the series getting smaller and smaller and smaller and smaller kind of as you go. And so that's sort of what I want you to think about when we work through the next problems. All we have to do for the next few is decide whether or not these converge or diverge. And we can just, that's all we're going to be writing is, does this converge or diverge? So I want to think about the things that we just talked about. So for example, I'm going to do this kind of out of order a little bit, because if I see automatically, like number 6 stands out to me, if I see automatically that I have a D involved, now it says assume problems 5 through 8 are infinite, and so problem number 6 is within that. I have a D involved, so this must be an infinite arithmetic, and if it's infinite arithmetic, it automatically diverges. So that's it for that. That's all I can say. Another one that sort of stands out to me is actually problem number 12 for the same reason. See this form here? That is more like an arithmetic explicit form where you have a sub 0 plus dn, or dn plus a sub 0, however you write it. And this is the form that we have here. Instead of n, we have I, but kind of the same thing, and then infinity up here. And so because this is arithmetic, infinite arithmetic again, we can go automatically and say that this one diverges. So that one I've got out of, those two are out of the picture right now. So let's look at some other things. And there might be more arithmetic in here. These were the two that stood out right away. Another thing that stands out to me right away is the ones that are finite. Finite are always going to converge. So then I'm going to look at these. Well, finite means it ends. Are there any series listed on this page that end, that are finite? Well, 4 is a finite series, and so therefore I know that it converges. It has a sum. And another finite series takes me down to problem number 11, because this top number doesn't go to infinity. So it's going to converge automatically because it is a finite series. This is finite series that I'm looking at. Okay, so again, those are the ones that stood out to me as fairly obvious answers. Now I'm going to have to kind of go through the rest. So we'll take a look at them individually, and I'm going to jump into 5, 7, and 8. Those are easy for me to visualize. And the reason that they're easy for me to visualize here is because I know what R is right away. And if we talk about converging and diverging, remember that what I had to look at was R. If R, absolute R, is less than 1, it converges. If absolute R is greater than or equal to 1, then it diverges. So let's look at these pretty quickly. Again, we can answer pretty quickly. If it is, here's my R is 1/4. 1/4 is less than 1. Absolute 1/4 is less than 1, and so therefore this one converges. What is wrong with me today? Holy cow. Converges. Mistake after mistake. Ignore those scribbles. 7, same thing. Absolute R less than 1, it converges. I hope that makes sense when I'm talking about absolute value of R is less than 1. These are both positive, so it doesn't really matter, but they're fractions where the numerator is smaller than the denominator. So if I look at problem number 8, this is 2 over 1, and absolute R is actually greater than or equal to 1 here. 2 is greater than 1, and therefore we say that this diverges. So again, I know I'm not doing this in order, and I hope that doesn't bother some of you who are pretty particular. We need to go in order. I just like to pick out the ones that are the easiest to do right away. That's just kind of my style. I get a little lazy. Anybody that knows me as a teacher has heard me say that I'm lazy, so I try to take the easy way out. So in taking that easy way out, I'm going to go down to 9 and 10 again, and I'm going to answer those right away too, because these are in the form of an explicit form for a geometric series. They have this power on them here. That power, they use a different letter, k minus 1 and m minus 1, but that power tells me that I am in geometric form. I have a geometric sequence. And so in this case, my first term is negative 1. In problem number 9, negative 1 is my first term, and my r is 1/2, and therefore this one converges because absolute r is less than 1. In number 10, my first term is negative 4, and my r is 2, and because, again, I have to look at the size of r, absolute r here is greater than 1, that makes this one diverge. All right, so now we're down to 3 more problems that we have to do, and on those 3 problems, we just have to kind of think about what's going on in the problem. Remember, if it is finite, it automatically converges. Well, the last 3 problems we have left are all infinite, and I know that because they all have dot, dot, dot on the end. Okay, so then I'll look at the sequences that are left. Are any of them arithmetic? Well, this one looks like I am multiplying the denominator by 5, so that means my r is 1/5. Okay, so that one's definitely geometric. The next one here, it looks like, what am I doing? 3 must be plus 9, maybe? Plus 9, plus 9. Yep, that looks right, plus 9. So this one's definitely arithmetic. I've got a D of 9. And the problem number 3, that last one, it looks like, again, if I put this over 1, I'm multiplying by 5 in the denominator again. In fact, more specifically by negative 5. So my r is negative 1/5 that time. So I've got infinite series. The problem number 2 is arithmetic. And an infinite arithmetic automatically diverges, so we can answer that one. But our last 2 problems, 1 and 3, those are clearly geometric. We have an r for them, and that's a common ratio for them. So I check the size of r. Is absolute r greater than or equal, is absolute r less than 1? In problem number 1 it is. So we say converge. And likewise, problem number 3 is absolute r less than 1. Yep, absolute value of negative 1/5 would be 1/5. 1/5 is less than 1, and therefore this also converges. Okay, so we sort of went through that a little bit fast, but we're just looking at converge and diverge. And remember, if it converges, it has a sum, and if it diverges, it doesn't have a sum. So that brings me to our next page, where we're actually going to find the sum. And so the sum of an infinite series. Well, we talked on the other page, if it is in fact infinite, in order for it to have a sum, number 1, it must be geometric. And then 2, once we know it's geometric, absolute r has to be less than 1. If these 2 criteria are met for our infinite series, then we can use that sum formula that we developed yesterday, and that sum formula is a sub 1 over 1 minus r. I hope that looks a little bit familiar to you. If it fails on either of these, then we say that the sum does not exist, or there is no sum for that problem. So now we're just going to put that all together and do a little math. You may want to have your calculator handy, but we have to look to make sure that the criteria are all met. So we have to state whether each infinite series below converges or diverges. Well, first of all, I know it's infinite, so I have to figure out, is it geometric? I know this first one is geometric, so the first criteria is met. So geometric, yes. And then is absolute R less than 1? So this is geometric. Check. And absolute R is less than 1. Yes, 1/3 is less than 1. Check. And therefore I can do the sum. So my sum is equal to 108 over 1 minus 1/3. And then I just go ahead and do the math on that. My sum is equal to 108 over 2/3. And so then my sum is equal to 108 divided by 2 is 54. 54 times 3 is 162, I believe. You guys can double check the math and yell at me later if you want to. I'm going to do that again. So 50 times 3 is 150. And then it was 4 times 3 is 12. Yeah, so I'm pretty sure that's correct. Scold me through email if I'm wrong, but I'm pretty sure that's correct. So that's what we have to do. We just have to go through and check. Is it geometric? Is the R the right size? Okay, so let's go on to number 14. Is it geometric? Yep, the geometric part is covered. Geometric, check. But is absolute R less than 1? Nope, this is where it fails. It is not. Absolute R right here is greater than 1, and therefore we have no sum. So if it converges, find the sum, and if it diverges, where does it fail? So this diverges. R is too big. It's kind of an easy way that we could just state the failure on that one. So it diverges because R is too big. So let's go back to number 13. We should have stated that this, because it says state whether the infinite series converges or diverges, this one converges because the criteria was met, because it does have a sum. Okay? So let's kind of go through that again with number 15. Number 15, it is geometric, yep, and R is the right size, so this converges. And it converges to the sum. The sum is negative 5/4 over 1 minus 1/3. And again, we've got to do the math on that. So negative 5/4 over 2/3. I'm going to go ahead and simplify that. I'll flip and multiply, and so it looks like negative 15/8. Again, you can check my math on that if you want to. Moving on to number 16, same thing. We can go through these fairly quickly. Does this converge or diverge? Well, it's geometric, but R is the wrong size, so it diverges. And we say absolute R here is greater than or equal to 1, that negative 2. I didn't want to say it was too big there. I know that's what I said on the last one. That one worked pretty easily because R was 4, and 4 is bigger than 1, but here it's negative 2, and negative 2 is not bigger than 1, but the absolute value of R is greater than or equal to 1. So maybe that is a better way to write it when we do it. Okay, so those were kind of easy to tell that they were geometric because they had an R in them. What if it doesn't have an R in it? What if I'm going to be the one that has to decide? Well, we did that a little bit already today, or yesterday, I mean, in notes, because you can find what R is pretty easily. And on this one, it looks like I am multiplying the denominator by 3. The top is staying the same, but the signs are switching, so my R must be negative 1/3. And I hope what I did, my sort of talk through that, made a little bit of sense. So this is geometric, and that works. It's times 3 in the denominator all the time, and so times 1 in the numerator all the time. So R is the right size. It is geometric, so it converges to the sum. The sum is the first term, negative 1/2, over 1 minus negative 1/3. So I'm going to have negative 1/2 over 3/3 plus 1/3 is 4/3. And when I do the math on that, I get negative 3/8, I believe. Again, if I'm wrong, you can scold me later on. But this one converges, and it converges to negative 3/8. When I look at problem number 18, I'm going to go through that same sort of process. I need to find what my r is. I notice that this is definitely shrinking. And so I can put if I can't tell what the r is right away, I can just put the consecutive terms, the second over the first. That's negative 4 over negative 6. That should be the same as negative 8/3 over negative 4, which should be the same as negative 16/9 over negative 8/3. And if you do the math on all those, I get 2/3 for my r. R is the right size, so good. That means that this is A, geometric, and r is absolute r is less than 1, so it converges, and it converges to the sum. The sum is negative 6 over 1 minus 2/3. That is negative 6 over 1/3, or negative 18. That one looks sort of familiar. I think we did that in yesterday's notes in the packet. So our sum here is this series converges to negative 18. What I'm saying is this series, if I could continue it infinitely and add the terms all together, they would add up to negative 18, or they would approach negative 18. So let's keep moving. Number 19. Looks geometric to me. Looks like r is 1/5. Remember, this is over 1, and the denominator is changing by multiplying by 5. The numerator is staying the same. R is the right size. This converges. It converges to the sum. The sum is 1 over 1 minus 1/5. That's 1 over 4/5, which is 5/4. So it converges to the sum of 5/4. Number 20. Look at what's going on here. It looks like it's growing. Actually, it looks like it's bouncing back and forth. It definitely is geometric if you look close enough that you can see that there is an r, a common ratio, and my r is negative 2, but absolute r is greater than or equal to 1, and therefore we diverge. And there's nothing more I can do. Once I recognize that it diverges, and that is it. All right, we're down to the last few. I hope you're still hanging out with me. All of them are infinite. All of them are in sigma notation. And some people get a little intimidated by sigma notation, but don't. Please don't. In fact, I think sigma notation is really easy to look at. The one thing that you do have to make sure of is that as long as n starts with 1, then that number in front is a sub 1. If n starts with 2 or 3 or 4, then the number in front isn't necessarily your first term. And so you're going to have to expand it out. You have to be real careful with that. That's not something we trick you with here in pre-calc, but it is something that I know I've witnessed in calc when I've worked in calc. So as long as n equals 1 for the starting, that number that hangs out in front is my first term. Okay, but what I'm really interested right now is the r, and the r here is 1/2. That r is the right size. Absolute r is less than 1, and so my sum is going to be, that means this converges, and my sum is negative 48 over 1 minus 1/2, which is negative 48 over 1/2, which is negative 96. So it converges to negative 96. Problem number 22, another similar one. Again, as long as that starts at 1, then that first thing is my a sub 1. It looks like my r again is the right size. Absolute r has to be between negative 1 and positive 1, and this is 2/5 fits the bill. And so my sum is, that means this converges. That means it has a sum, and the sum is negative 9/5 over 1 minus 2/5. And again, now it's just a matter of doing math. Negative 9/5 over 3/5. I'm just doing the math here, nothing fancy, and I end up with -3 when I do the math on that one. So this one converges to -3. All right, we're down to last two. The last two are going to finish up pretty easily because they are in the right form. I do have an a sub 1 here because this starts at 1, but if I look at r fails me. Absolute r is greater than or equal to 1, and therefore this diverges. R is the wrong size. R has to be less than 1. Absolute R has to be less than 1 in order for it to converge, and this one fails. Looks like the same thing on the next one. Absolute R is greater than or equal to 1, and therefore this diverges. So that is really it for this chapter. We are done with this chapter. Tomorrow you are going to get a review, and on Friday, you will get your test. So yeah, your homework tonight is to do, for my class, you are going to do the odds on 7-4, and for Fauser Vasquez, you are going to do the evens on 7-4, I believe, unless they tell you otherwise. So thanks for joining me in the video, and you guys have a fantastic day.